dimension reduction or dimensionality reduction. Have you guys heard about things such as data compression, compaction? Have you done anything like that before? For example, use zip, right? You did that before, right? You will be asked how you want to compact your data. And there's something else, for example, for images. If you have very large images, there's a lot of tools online which you can upload one image and the website can compress the image for you, right? That will sacrifice the resolution a little bit, but you can still see the major features in the image, right? And different compression methods, they're just different ways of remove less significant data from the image. And that's exactly what we will be talking about today. That's for dimensionality reduction or dimension reduction. And for this lecture, because we have a lot of math in it, which we cannot skip, so we have to switch back to the note way of doing the lecture. And for this lecture, we have two objectives. The first one, after the lecture, you guys need to be able to explain the idea of dimension reduction and list popular dimension reduction methods. Second objective is that you will need to be able to derive and implement two very popular dimension reduction methods, PCA and LDA. PCA here is for principal component analysis, and LDA is for linear discriminant analysis. And we will spend more time on these two methods. First, let's talk about the basics of dimension reduction to give you guys some very general ideas about what is dimension and what it looks like and what will happen to the data if we take some dimension reduction operations. My notes will roughly follow the book, but you will find some deviations. First, before we start talking about how we can reduce the number of dimensions of the data, let's take a look at the data first. Actually, in different chapters, you will see that we try to arrange the data in the same way. With data, depending on what we're talking about, supervised learning with labeled data or unsupervised learning with unlabeled data. Here we're talking about unsupervised learning, so we only have unlabeled data. We only have the X bar. Here X, we use the capital letter X. X bar, the unlabeled data set, consists of many unlabeled data samples or instances. So we have X, each of them, originally they are a column vector, but in this capital letter X bar, we put them as a row vector. That's why we need to have a transpose here. And we said that throughout the lectures and the book, you see that we have capital letter I samples in the data set. And because all of them transposed, so they are now row vectors. Row vector, we stack them together, so they will form a column vector. So we have another transpose operation here. So actually, they should look like this. X1 vector transposed, X2 vector transposed, and Xi vector transposed. And if we write everything out, they will look like this. X11, that's the first element of the first sample. X12, that's the second element of the first sample. We spend the time to talk about this, and we usually say that we have capital letter J attributes. So that will make each sample have J elements. Second one, we have capital letter I samples. So we have Xi1, Xi2, last one, Xij. Finally, for the whole unlabeled sample array, we will have I rows and J columns. Again, just keep this in mind. We are talking about attributes. So this is attribute 1, and here's the last attribute, J. Again, we have J. Here we say J attribute, attributes. So we are talking about dimension reduction or dimensionality reduction. Actually, we are talking about how to reduce the number of dimensions. Here's the dimensions actually that correspond to the attributes, the features. So this is the dimensions. For example, if we have 3 features for the unlabeled data. That means we have 3 dimensions. If we plot everything out, that also means that you have 3 axes in your plot, right? 3D. Here, for every row, we have 1 sample. So this is sample 1, and it is x1. Because it's x1 originally is a column vector. Here we list it as a row vector, row array. So we should put a transpose sign here. It's sample 2 and sample I. And I think this is the number 1 thing that you need to keep in mind. Here for data, we have 2 things. We have 2 dimensions. We are talking about the rows in this capital X bar. We are talking about different samples, columns. We're talking about different attributes. Here, when we say we want to do a dimensionality reduction, actually we want to reduce the number of columns, the attributes, not the number of samples. That they're not the same thing. For example, if I say that I give you 100 images. That's a data set, right? Each image has a size of 227 by 227. Now I said that, could you guys compress the image data for me? I'm not asking you guys to reduce the number of samples, to reduce it from 100 images to 20 images. No, that's not data compression. What I'm talking about is that now shrink the images, right? Not 227 by 227. Now reduce the dimensions to like 40 by 40. That is dimension reduction. That's attributes. So let's write it down to emphasize this fact. Dimension reduction. We are talking about reduce the number of, here's many things. They can be used interchangeably in the context of dimension reduction. Here we could say reduce number of dimensions. Of course, that's the word that we use in the title. And we know that the dimensions in such a context correspond to the number of attributes. We know that another word for attribute is feature. There's some minor difference between them, but here we don't differentiate these 2 words. And we are talking about plotting, we use the axis. But you may ask, everybody can do that, right? You just cut off some attributes. Then what is the trick in doing dimensionality reaction? The trick is that we want to make sure that we will not lose the major information, right? Not every number, not every element in the array is equally significant. They are different. They may contribute to the overall characteristic of the data in different ways. So we want to make sure that we will maintain those attributes, those dimensions are more significant. So here's something we keep in mind. We do this reduction in the number of dimensions, attributes, features, and axes without losing the essential information in the data. And then how to do it? That will determine what type of dimension reduction method that you will use, right? So here we talk about a classification of dimension reduction methods. There are 2 major categories. The first one, actually, I just mentioned it, is called that feature selection. Feature selection is attribute selection, dimension selection, right? That means we just select some attributes, some dimensions we think that would be more significant than the others, or would be more essential to the overall characteristic of the data than the other. And for this one, again, it's called feature selection. So we select some attributes to keep and remove some others. Select or keep most significant attributes. So when we are talking about the most or more, actually usually we have a bar or threshold to determine how significant is enough. That will also determine the level of dimension reduction that we want to do. You can do it on different levels. But the higher level, the more in-depth dimension reduction that we want to do, that means more attributes that we will remove. In that process, it's likely that we will lose more information. This is the first category. Second category is called feature extraction. They may sound very similar, but there are some distinct differences between them, between these 2 categories of method. For this one, we're trying to extract the most significant dimensions, which are the combinations of some basic attributes. And such significant dimensions, they are not necessarily directly from the original attributes. They can be combinations of them. So let's draw a figure to understand it in a simple way. Let's say that if the original data has 6 dimensions, so let's put it this way, let's draw 6 different directions. We can understand it in a very simple way. Use the same data for both feature selection and the feature extraction. And what feature selection does is that originally we have 6 attributes, right? Let's say that we want to remove 3 of them and keep the other 3. In feature selection, what we do is just, for example, we select these 3. 1, 2, 3. That's it. But for feature extraction, the idea is slightly different. Instead of using the existing ones, it's more likely that we will explore new directions or dimensions as the combinations of the existing ones. Then we will project the existing data set to the new dimensions. So we may select new ones, and then there's a relationship between the existing axes or dimensions with the new ones. That is feature extraction. Next, let's take a look at the feature selection. There are many different ways that we can do it. So here I will talk about 6 of them. The first one is called missing value ratio. It is very common in engineering that when you get some data, for example, from the lab, you will find that, oh, you may get a lot of missing data points. Not data points, but missing numbers. And they can be represented depending on what software package that we use. They can be used NaH, NaN. Have you guys seen such things before? Or sometimes they may use null. For example, you use pandas, you may see NaN. That means there's no number, no meaningful number there. That can be caused by the malfunction of the measurement device, right? It does not function, does not give you any readings, so you get nothing there. So if you get a data like this, and you have a lot of empty elements, there's nothing there, no meaningful number there. In that case, one easy way to tell which attribute that we want to remove is that you take a look at different columns of the data and see if one column has a lot of missing elements. Then one intuition is that, oh, we can just remove that column, right? Remove that dimension. When it only has a few elements missing, 1 or 2, you may just feel 0 or some other things. But when there's a lot of missing data, it's a very common selection is that we can drop the attributes with lots of missing values. Here again, we're talking about drop one column, one attribute, not samples. Here we know that for every attribute, different element will have different attribute values. For some elements, the attribute values may be missing. That's why we have a lot of missing values here. That's the first one. Second one is called a low variance filter. These feature selection methods, they are very straightforward. So here I just talk about the idea. The core idea of the use of low variance filter for feature selection is that, for example, we can calculate the variance of different attributes. So if for attribute, you can get a variance value, then what you can take a look is, to compare different variance values of different attributes. If we have lower variance in the low variance filter method, we will believe that the data points, they will stay closer along that attribute, that dimension, closer along that attribute. Put it right here along that attribute. I'll skip it here. And that means we have less information. If less information, we want to keep the attribute that will carry more information. So we will remove this attribute as a relatively low variance. So remove it. And that's the idea of low variance filter. Next method for feature selection, it is called high correlation filter. And this one is also very straightforward. That is that if you compare different attributes, you will get, it's not difficult to get something called the correlation coefficient or parameters. You have a high correlation coefficient. That means two columns, they are dependent of each other, right? If we have a 100%, an easy way to understand that these two axes, we have the same, they are exactly the same, right? If they are exactly the same, then why do we keep this attribute? Just remove it. So if two attributes have a high correlation coefficient, that means they may be highly mutually independent of each other. In that case, we can remove one. Next, we can also use one decision tree algorithm that we introduced before, the random forest, to do the feature selection. We do this because if you're thinking about the random forest or decision tree in general, you possibly still remember that we need to select an attribute, a feature at any node inside the tree to do the data splitting, right? We need to see which one will give us the best improvement. We want to improve the data purity, And for this one, what we do is that we can take advantage of that because we have attribute selection for data splitting. We can just take advantage of this step. We can look into those features that can give us, for example, higher Gini index. Another thing that we can also take a look is the out-of-bag error. Actually, if you are using scikit-learn, the decision tree can give you the out-of-bag error directly. And these two things, they are related to the significance of the attributes. And we know that we want to keep the more significant ones. That is random forest. Another two common feature selection methods are backward feature selection and forward feature selection. These two are not difficult to understand. For backward feature selection, what we do is that first we try to train a model with data that includes all the attributes. So let's say that we have J attributes, so you have J, it will keep all the J attributes when we are doing the training. The next thing, we try to remove one feature. So we're going to have J minus 1 features left over, right? If you take a look at the data here, you remove one column. We still have capital letter I samples, but we will remove one column from this array and do the training. So we will get J minus 1 models because we're going to get J minus 1 reduced data sets, right? For each of them, they have one column removed. And we will see which reduced model will give us the best performance or give the performance that is closest to that model is trained with the complete data set. So what we do is that we first train a model including all the attributes. At the very beginning, we have J attributes. Next, we train J minus 1 models with J minus 1 reduced data set. Your data sets, and each data set has J minus 1 attributes. And we will select the model that can give us the best performance or the performance that is close to that of the model that we trained with all the attributes. Here we just call it the best model. So in this way, you can see that we moved from J attributes to J minus 1 attributes. So we can repeat this process to remove more attributes. This is backward feature selection. The forward feature selection is performed in the opposite way. Instead of starting with all the attributes, now we started with one attribute first. So what we do is that we first train J models with J datasets. And each dataset only has one attribute. And we will see which dataset or which attribute gives us the best performance. and we will select that one. And then we will repeat the process. In the next iteration, we will try to add one more attribute to the one that we selected in the first iteration. And then we repeat this process. We can add more and more attributes. We train J models with J datasets, each of which includes one attribute. We select the model with the best performance. Next, we just need to repeat this process to add more attributes. And these are the 6 common feature selection methods. Let's take a look at feature extraction. Again, feature extraction is much different. Instead of try to select from the existing attributes, we're trying to find a better projection directions. So each new projection directions can be viewed as the combination of the existing directions or dimensions. For this one, we will list the most common methods here, and later we will spend more time on 2 feature extraction methods, PCA and LDA. So for feature extraction, of course, PCA and LDA are possibly the most well-known ones. And other than that, we also have many other options such as ICA, LLE. You can go to the textbook to get the full name of it and also get more information about each method. We also have something like ISOMAP, MDR, and kernel PCA. Another thing people will talk about a lot when we're talking about dimension reduction is that whether such method is linear or nonlinear. The first 4 feature extraction methods here, they are linear methods. And the last 4, they are nonlinear. And you can see that we have the kernel PCA is nonlinear while PCA is linear. The reason is that we're adding the kernels, which can give us the nonlinear capability. We did this in previous chapters for other machine learning topics such as linear models, such as supported vector machines. So this is a common way to go from linear and to nonlinear by adding the kernels. And here I also want to use one example to see how we can easily do the dimension reduction. So we come back to this X. We know that we have an array I times J. That's the shape of it. Now we can think about one thing. If we are talking about finding the new directions or dimensions, we can use a new matrix. Let's call it capital letter W bar. It has a shape like this. It has multiple column vectors. Each column vector, small letter W vector, is a direction or dimension. If we write the full array out, it's going to be like this. W1, 2, 2, 1. The shape of it here need to have J rows. And for the columns, let's call it L. Later you will see why we need to have J rows. And as I said, each column is a W, so this is WL vector. And this is W1, W2. The reason that we wanted to have the shape like this is that we want to go from the original data set with all the attribute to a new data in a new low dimensional space. The easiest way of doing that is doing it this way. Let's just say that the new data with the reduced dimension, let's call it the Z, capital letter Z bar, can be obtained by multiplying the original data with this W. Original data X, we know that it has shape of I plus J, and here W here has J times L. You can see that these two need to be the same so that we can have this dot product. And for the new data, now it should have I times L. I, that's the number of samples. So you can see that originally in X, we have I rows, so we have I samples. Now we go to the new sample, we still have I rows, so we have I samples, but now the dimension L is different because now we are talking about dimension reduction, right? So L should be smaller than the original dimension is J, so that in that way, will make sense. In later introductions, we will not use L, we will use J prime, but it's the same thing. So what we did here is just to map data to space represented by this new vector W bar, and it has the shape of J times L. You can understand it this way. These J columns, they can be viewed as the J axis of the new coordinate system in the lower dimensional space. But since L is smaller than J, so the new space, the new coordinated system should have lower dimensions. Next, let's take a look at the two feature extraction methods that we need to know about. The first one, again, is called PCA, or Principal Component Analysis. From its name, we can see that we're trying to find the principal or the major components. The other one is LDA. Here we want to take a look at one figure to get an understanding of PCA and later and the LDA, which will be introduced later. Let's see the idea of these two feature extraction methods and see what differentiates PCA from LDA. This is a big picture. So we can see here in the figure we have two clusters of data, one in blue, the other one in green. The idea of PCA is that we want to project these two clusters of data, groups of data, onto a new lower dimensional space. So here you can see that this is a 2D problem. We have E1 and E2. They are two axes, two dimensions of the current space. And the current space has two dimensions. If you want to reduce it, the only way that we can go is just reduce it from 2 to 1, right? And you want to reduce it to a one-dimensional thing. And 1D, we know that if we want to plot it out, that's going to be a straight line or a curved line, right? Here we are talking about a straight line. For the straight line, we can use one vector to represent it. Let's now call it W1 vector. So this is line. We project all the points, data points, to the new space. Then all the points will be distributed on this line represented by W1 vector. The idea of PCA is that we want to make sure that the points, they are scattered everywhere. That means we want to make sure that they are scattered over a large area. This will make the projected data points have a larger variance. They're scattered everywhere. If all data points in the lower space, in this line, they cluster together, that means they have high variance. And that's not what we want. We want to do it in the opposite way. And for this one, PCA, one thing we need to make it clear is that it deals with data that is not labeled. So here you can know there are two classes of data, but when we're doing PCA, we don't necessarily know the labels. We assume that all the points look the same. And with criteria that here we want to use that, we want to make sure the points in the lower dimensional space, we want them to spread out or have high variance. This is one way to understand it. The other way to understand it is that we want to make sure that all the points are close to this new space, this line here. But in that case, we want to do one thing first. We wanted to do something called zero centering. That is, we want to find the center and then want to make sure this line will pass through. And that's actually what we will do later. Here, I'll move you here. Just want to help you guys easily visualize the problem. That is for PCA. LD is done in a totally different way. First, it is used to handle labeled data. So if you want to use LD, you want to make sure you know the labels. And if you don't know the labels, you would know, for example, how many classes you have. Here it's obvious that if we know the labels, we know we have two classes. For LDA, what we want to do is that we want to make sure that the data in the lower dimensional space, the projected data, they need to be separated as much as possible. If we want to make sure that projected data points can be separated in the best way, actually here we want to do it by inserting two things. First is that the centers of the two projected data classes should be far from each other. That's one thing. The second thing is that we want to make sure that each class of projected data points, they should cluster together. So we should have low variance for each, because each class, they have their own data points. Then they have their own variance value. Here, this is another variance value. This needs to be low variance. And this one, distance between the mean vectors is large. And this is difference between PC and LDA. Another thing everybody need to know about, and this is very significant, is a few parameters. In the original space, let's say that the center of each classes of data, let's call this one mu, this is class 0, this is mu 0. We put a vector sign here because it's the location of the center. This one's mu 1. And for every point, let's take a look at this point. For every point, its location in the current x, here from this point from the origin to the center of the data point, this should be, let's call it xi vector. And we wanted to project this data point to a new lower dimensional space. For example, we are talking about W1 is the space that we want to project it to. So it's gonna be here. And let's say that if this line is distributed here, for example, it's distributed here, and this line, then this point is gonna be here. Sorry, this is not a good example. Let's assume that, because this is a 1D space. If the center is here, this vector should be here. Then this is you're gonna use another sign for it, the Zi vector. Here we are talking about a single point, so we use a vector instead of bar, and we need to mark with the number of the data point. One more thing that we need to pay attention to, we want to project this data point back to the original space. So if that's the case, for example, we are talking about a data compression. We first compress the data. So every data point in the original data sample, they have their own location. When you make the compression, it will have a new position in the new data set. But sometimes we want to do the unzip and to do the extraction to get the data back to the original size. In that case, here gonna be the new thing. We call it X vector, but we put a hat above it. So this is the new, if we project it back, it's gonna have a location like this. Then let's take a look, PCA, how we're gonna do it. First, the goal, we just to talk about it. We have two ways of doing it. The first way is we want to make sure that we have the maximum variance for the projected data points. Or we can want to make sure that we have the minimum distance between the original and projected data points. As I mentioned, when we're doing the real PCA work, we first need to do the centering. So make sure that this W, this new line will pass through the center of all the data. Next, we do the projection. We need to select one direction and project all the points onto this X. And we want to find a direction that will give us the lowest total distance between all data points and the X. So for each data point, it has its own projected data points on X, and we can get a distance. We need to add all the distance up to get the total distance. And these two, we just need to satisfy one of them. In your book, actually, I show the direction for both, but here we will go with the first one. We'll try to derive the theory for PCA based on the first goal. Few other things that we need to do. First is the pre-treatment. That is, we need to do zero centering. It's very simple. We just need to subtract all data points. Subtract the center from all data points. So for every data point, xi vector, we need to do it in this way. It's gonna be this vector minus the center of it. It's just center is the average. Here we have I data points, so it's 1 over I. And here we have a summation. Smaller I go from 1 to capital letter I. and we want to do the summation over all data points. That's how we do it. And after we do this pretreatment, zero centering, we should have the following thing. That is the summation of all the new data points or the new zero centered points. They should have the mean at 0. So we add them up, we should get a 0. And let's take a look. Let's take a look at the projections I just mentioned. And actually this is valid for all the dimensionality reduction based on projections. The first projection that we want to do, we want to go from the original data x bar to its corresponding projected data in the lower dimension. Let's call it z. Z is done in this way. So just don't look at the dimension. We can work on it later. Originally, x has I rows and j columns. That is I samples and j attributes. We want to find a new space. This one should also have j rows, but here let's don't use L, let's use j prime. J prime need to be smaller than j, so we can have a reduction in the total number of dimensions. And as said, we're talking about data compression. We first want to compress the data, then we want to extract data out to its original size. So we do the uncompression or the extraction. We will get this x bar. Bar will be different from the original data x bar hat will be different from the original data x bar because it has gone through one compression process. So some information will be losing in that process, no matter how careful we tried it to be. And for originally this should be I times j prime. So you can see that j, then you will have j prime attributes, which is smaller than j attributes in the original data. So we do the data extraction with uncompression. We start from z bar. It has I times j prime. The shape of it, what do we need to do? We just need to do this wj attributes. The reason that we can do it is that because j, this vector will consist of vectors, unit vectors for all the different axes, and each vector, all the vectors should be orthonormal. That means they are normal to each other. Because of that, then j bar transposed equal j bar inversed. The inverse of, w bar transposed equals w bar, the inverse of w bar. As if these two conditions can be met. Actually, that's what we are trying to get. So this is the projections. Next, let's do the deduction. Let's show how we can get the equations that we will need for performing PCA. As I mentioned, we can do the deduction based on the maximum variance or the minimum distance. They are equivalent. Here we will do it based on maximum variance. To maximize the variance, let's take a look what the variance would look like. Here's the variance of the projected data. The variance of the projected data points would be like this, based on the definition of the covariance matrix. Here, when you have the variance between two 2D arrays, because both X build their 2D arrays, so the projected data Z will also be a 2D array. For 2D array, the covariance matrix will be 2D. It can be obtained in this way. So Z actually equals X bar, W bar, that's Z, minus, because the center is 0, that's how we get the covariance matrix. Here we have two zeros, that's the center of it. Then we will have this. And we know that this is just Z transposed dot product Z. Next, let's take a look at the PCA problem. It can be described as a constraint optimization problem. Here, PCA problem means we're trying to solve a dimension reduction problem using the PCA method. Is the following constraint optimization method or problem, So we are trying to find the best W bar, the low dimensional space that can help us maximize the variance. But here, the covariance is just the matrix. We just want to minimize or maximize one thing, a single variable for the optimization problem. So here, what we do is that instead of maximize the whole 2D array, here we want to maximize the trace of it. The trace, that's the summation of all the elements along the diagonal of the 2D array. Here we use TR to represent the trace, so it's a summation operation, but it's summation of just elements along the diagonal. Again, this is the constrained optimization problem, and here the constraints is that the 2D array W should be orthonormal. That is, W transposed dot product W should be equal to an identity matrix. The shape of the identity matrix depends on the shape of W and the W transposed. Here we know W has the shape of J times J prime, so this one should be J prime times J. In this case, I should have a shape of J prime times J prime. So if you want to see what it looked like, it's going to be like this. You have 1, and it should have J rows times J columns. All the elements of the diagonal should have a value of 0. But we said that usually we want to deal with minimization problem instead of maximization problem. To do it, we just need to make a very minor change. Here, this can be done by add a negative sign here. And if we want to convert this constrained optimization problem into a unconstrained one, we can use the Lagrange multipliers that we talked about before when we are introducing the support vector machines. To do that, in the new one, it can have a loss function like this for the new unconstrained optimization problem. We just need to add this into the loss function. So in this minimization problem loss function, this, if we add constraints to it, we just need to add the Lagrange multipliers. Let's call them lambda. There are many of them. To add them, we still have trace. But if we add it directly, you can see that this gonna be so we will only have lambda times WT dot product W minus I identity vector with here's the identity matrix with the shape of J prime times J, but it's also a vector. So we can do one thing, that is, we can, instead of do everything, we can also do the trace thing. So we have the trace of the two terms. And we know that J reaches the minimum or the optimum value under the condition that the derivative of J with respect to W should be equal to 0. So the optimum point or the lowest point occurs when the derivative of it, that's the slope of it, equal to 0. So it's flat. And the slope is flat. Here you will talk about different point, it's not flat. We go here, it's flat. So the solution to the above optimization problem is the derivative of J. Here we want to optimize W. So let's get the derivative of J with respect to W. W is a 2D array. Here we use transpose. It will be the same thing. And if we get this, the derivative of J with respect to WT, we will get the following things. That is, so we'll get the derivative of this part, then we will remove this W, and the second one, we'll remove this one. Plus, and here's identity matrix, so the derivative of I with respect to W will be 0. So we only have one left over. This will give us one thing. Sorry, this is wrong. So this is the first term. We get this off. The derivative, second one, get this off. We have this and the less left over. And if you take a look, you will find this is a very typical eigenvalue problem, right? For eigenvalue problem, we solve it. We will get here, because W, if you take this, both of them have a shape of J times J. Is J times J prime. Is also J times J prime. And if we solve the problem, we will find that we need to get the eigenvalues and the eigenparameters of this. of X transposed dot product X. That will give us J eigenvalues and J eigenvectors. But we know that what we need is we want to get to J prime, which represents the new low dimensional space, right? Then this one is composed of the eigenvectors corresponding to the first eigenvectors of X bar transposed dot product X bar. If you know W, then you can do everything. You can do the two projections, right? You can project one data set to the low dimensional space, and then you can also project it back to the original space. In that way, we do the compression and uncompression. The final, let's summarize everything by laying down a procedure to do the implementation. And you will need this to develop your own code for implementing PCA. In the procedure, we need to do a few things. First, we need to do the zero centering, right? And this one, we know that we can do it in this way. Or if you want to use the NumPy operations to do this, you can use X bar directly. X bar equals bar minus. We can do it in this way. We can do, because for all the samples, the mean we are talking about, we want to get a mean of every attribute values. That's every column. Column is x1, so we want to get NumPy mean method out of it. And here it should be the axis should be 0. If we do it, then we will get a mean for every column. That's for every attribute. So for attribute, we add up all the samples divided by the number of the samples. Second, we want to calculate the eigenvalues and eigenvectors of X bar transposed dot product X, and this one has shape of J times J. Here I mark the shape out is to facilitate your implementation. So you know that for each step you do the calculation, you take a look at your results. In the variable explorer, you will see the shape of it. If it's different from what I gave out here, then you possibly did something wrong. Third, we get all the eigenvectors. We want to number all the eigenvalues. For example, from the maximum one to the lowest one. And their corresponding eigenvectors will also be reordered based on the order of the eigenvalues. Each eigenvalue has its own eigenvector. And with all the eigenvectors ordered by the values of the eigenvalues, we can select the first J prime major eigenvectors and let them deform this W. So obtain bar, that is the 2D array that we use to represent the lower dimensional space, which has J prime axes with dimensions. And these J prime axes will be the J prime major eigenvalues of what we just obtained in step 2. Last step, we can do the projection. So if we know X bar, that's origin data. If we want to get the data in the new space, then it's going to be Z bar equals X bar times W bar. Then if we want to project the data from the lower dimensional space back into the original space, we have X bar hat equals Z bar times W bar transposed. And this is how we do the PCA. For LDA, again, LDA is short for linear discriminant analysis. The goal of this one, now there are two, but the relationship between them is and, not or. Both of them need to be satisfied. Now, because we are dealing with two labeled data, so we want to make sure that the projected data, they can belong to different classes. They can cluster together tightly. To do that, first we want to make sure we have great distances between classes. Here's the classes of the projected data. And this distance is just distance between the mean vectors, the mu of different classes. Usually we say that we have each of them, the mu vector should be mu k vector, and the k, small letter k, go from 1 to capital letter K. So let's say we have k classes. That's the first thing. Second, we want to make sure that the data points, the projected data points in the same class, they should stay close to each other. So projected data points in the same class, close to each other. We know that when close to each other, that means the variance is small. So large distance between the mean vectors, but low variance, depending on we are talking about a univariate distribution or multivariate distribution. That's how many variables we have. If we have multiple attributes, then we have multivariate distribution. For multivariate distribution, we have sigma bar. That is the covariance matrix. Actually, we learned about this before. If we only have one variate, we use sigma. That's standard deviation. Alright, now we know the two goals that we need to meet. And again, this is different from P. The two conditions, they are equivalent. We just need to satisfy one of them. And the other one will be satisfied automatically. But here, the two goals, both of them need to be satisfied. We also need to deal with data pretreatment. Here we are talking about the zero centering. This will make all the later operations easier. And also, we need to talk about the projections. Here we have two types of projections. We project the data from a higher dimensional space to a lower dimensional space. That is the data reduction that we want to do. But in many cases, we want to project the projected data back to original space. That's the second type of projection that we may also need to do in many cases. And they are the same. The projections are the same as what we introduced for PCA. Alright, now we know the goals. We have the data that has been pretreated, and we know how to do the projections. With all of these knowledge and operations, we can do one thing. We can put together the loss function or the optimization problem. So for this one, first let's use binary classification as an example to show how to do this, do LDA. I'll show the deduction for binary classification problem, then we will extend it to multi-class classification. For this one, a LDA problem or a dimensionality reduction problem using the LDA method can be conceptualized as a optimization problem. This optimization problem, we are trying to minimize one objective function to get the optimal parameter bar. Here the objective function, it is a binary classification. So we want to project it. We can only do it from a 2D space to a 1D space. We will see that. For the objective function, because we need to do two things. We need to make sure the distance between vectors. Here we have two classes. So we want the distance between the mean vectors of two classes to make them as small as possible. So we can put this one in the numerator. And we want to make sure the covariance is as large as possible. So we can put this into denominator. 1, 2. So that we can combine two conditions into one equation. That's a very common strategy. If we do it in this way, first write down the distances between different classes. Here we have two classes, binary for a binary classification problem. Here we'll talk about projected data. So projected will be original data times the direction. The original data, the center, the coordinate of it is just mu 0 vector times the direction. We'll get the projected data. We want to get the distance. Here, let's use the second norm, Euclidean distance. And for the variance, we know the original variance here. So we also want to project it to the new space. To do that, we need to do it in this way. And the second norm, Euclidean off distance, can be further written as we can combine the two terms in the denominator. And you can see that this is the objective function. Next, we want to solve the problem because now everything looks pretty complicated. Next, let's do a few things to simplify the solution. We want to define two new parameters. The first one is called SB bar, so it's also a 2D array. SB bar, we define it as this. And we know that the original mu should have the shape of j times 1. Here we have a transpose here, so it's going to be 1. And then SB should have a shape of j times j. That's a shape. Another parameter that we want to define is called SW bar. SW bar is just this term, and this is SB bar. In that case, SW bar, if we write out here for the covariance matrix, it can be calculated using this. So first for epsilon bar 0, this one equals x minus I times mu t. Here I is a vector, has a shape of I sub 0, 1. Here I vector I bar, that means it's identity vector identity matrix. But this I without a bar or vector sign above it, that is the number of the samples. Here's the number of samples for class 0. That's the first class. Here we have a transpose sign here. This is also I sub 0 times 1. Again, that's the shape of this identity array. This is for epsilon 0 bar. Then for epsilon 1 bar, it is very similar. We just replace x0 with x1. Another identity vector here, it'll be I sub 1. That's the number of samples in the second class. And with the newly defined SW, SB, and SW, let's take a look at the optimization problem again. It will become this. And this term actually has a name. It's called generalized Rayleigh quotient. So for anything like this, it's called a generalized Rayleigh quotient, and it has a special property. The property of Rayleigh quotient is that this quotient, let's call the whole thing B, SW, and W, is determined by three things. This R thing needs to be smaller than the maximum eigenvector and larger than the minimum eigenvector of this SW bar B. You don't need to know how to prove this property. Here we just give it out directly. We just need to adopt the conclusion directly. So here I want to show how to prove that. You just know that for anything like that, the quotient, the R, this is the quotient, should be smaller than the maximum eigenvalues and the minimum larger than the greater animal. This is the eigenvalues of B inversed times A. That's the property of generalized Rayleigh quotient. But here we know that we are trying to get the maximum value of this quotient, right? To get the maximum values of it, actually what we need to do is just to try to get the eigenvalues of this one. But here we know that actually what we want to do is to get, let's say that if we only have one or two eigenvalues, then W just be the eigenvector corresponding to the maximum eigenvalue of this. When we have more than one dimensions, if we are talking about multiple dimensions, then we're gonna get multiple eigenvalues. So W, then in that case, will become W bar. It will be the major eigenvectors corresponding the first few maximum eigenvalues. Eigenvectors corresponding to the maximum eigenvalues. And this is for binary classification. For multiple class classification, and let's go to that one directly. So we're gonna have a few changes. First, this is the objective function. We will not have just one vector. We have multiple vectors. They will form a 2D array. So instead of have W vector, we have W bar. We still have SB and SW, but now SB and SW will be slightly different in the multiple classification condition. B bar will be calculated using this. IK, again, there's no vector or bar sign above it. That means it's the number of samples. In the kth category, here we can see a new thing called a mu, because we know mu k, that's the mean vector, the vector representing the location of the center of the kth category. But a mu is the mean vector for all the data points. So mu just this. Xi should be all the samples, summation of it. That's how to calculate mu. Mu k, you can calculate it in the same way as what we did before. So mu k is just the mean of the mu for the samples belonging to the kth category, small letter k, instead of the mean of all the samples. Bar is calculated using an equation that's very similar to what we did before in binary classification. The difference is that previously we only have two components corresponding to epsilon 0 for the first class and epsilon 1 for the second class. But now we have more than two classes. So we get a summation of everything. Depending on how many classes you have, then you're going to have capital letter K terms in it. It's I sub K times 1 times mu K. You can see that they're very similar between here and here. Just a more generalized equation. It's also identity array with the shape of I sub K times 1. And we know how to calculate SB bar and SW bar, and then we can rewrite this. And then we will find that here we have the W bar, right? W bar consists of W vectors. If you write them out, we will see that this will give us an array. So the objective function will not be a function of one variable, it will be a function of multiple variables. Usually we want to get objective function of one variable or a scalar instead of an array. To do that, a typical way of doing it is to do like what we did before, to get the trace of everything. But here we're not doing trace because trace is summation. Here we want to use another thing. That is the products of all the elements along the diagonal. So we're going to use this sign. Again, this sign means it's the products of all the diagonal elements. Here, if you put it in front of this, then it's going to be the diagonal elements of this. If you put it in front of the other one, it should have the same meaning. Then it's going to be this, depending on which variable that you want to put this one. And this can be further because there's two products, so we can simplify it. It's just this. It's a product. Let's go from I to J prime. So in this way, you can write as vectors instead of the W bar anymore. This is also the product sign. So this is what we need to know about LDA. Again, we are getting a problem. What we need to do first, we need to data treatment. We need to get to the zero centering. Next, we need to calculate SB and SW using these two equations. With these equations, then we can get the eigenvalues. So the procedure will be very similar. First, still zero centering. Second, get SB and SW. Third, solve the eigenvalue problem, right? So we will get all lambdas and the v's, the eigenvectors. Second, the ultimate purpose is we want to get this W thing. Depending on the J prime that we want to go to, so we want to select this J, this W will be the first, the J prime eigenvectors corresponding to the first J prime eigenvalues. So we want to get the eigenvalues of SW first, dot product SB. So the inverse of the SW dot product XB will give us an array of J times J. So we will get a J eigenvectors and a J eigenvalues. However, WB vector is made with this. So we have K, that's because we have K classes. That will determine that SWB will have K, the rank of this one will be K. If they only have K for the rank, then it will have K independent eigenvectors. That means when we try to get eigenvectors and then use the eigenvectors to construct the W bar, the new space, we only have K independent axes. So when we do the reduction, the dimensionality, we can only get K minus 1 for the low dimensional space. Then that's the maximum dimension that we can go.
I think I'm falling for you.